In this lesson, we'll talk about the introduction to vectors. Vectors in a plane. A vector is a quantity with both magnitude and direction represented by a directed line segment from a reference point O. As you all know from physics, you have probably discussed about vectors. It's a quantity that has both magnitude and direction. A vector in the Euclidean 2-space R2 has two components x1 and x2, or it may be x and y, or other variables. Take note that we call x1 and x2 as components, not as coordinates, unlike in analytic geometry. Okay, we use the word component. Here we have R2 is a set of vectors with components x1, x2 such that both x1 and x2 are real numbers. A vector can be named using any of the following. You may use a bold lowercase letter like U, V, etc. You can also use capital letters as long as it is in the bold phase. Or it can be written as a letter with arrow above, just like this one. Vector A, vector B, vector U, vector V. You can also write the vector with harpoon, just like this one. Okay, if you're familiar with this. Alright, here in the illustration on the right, we have vector U. Okay, in illustrating a vector, just simply plot the terminal point of the vector. In this case, the terminal point is xy. So we just connect the origin to the terminal point. And then that is the illustration of our vector. Take note that the vector has an arrow. It is actually a ray instead of a directed line segment. Okay, vectors can be written in this form, in matrix form or parenthesis form. Also, equivalently in other texts, they use the angled bracket, like this one. The magnitude of vector U in R2 is given by, okay, we have the double bar symbol to represent the magnitude. This is equal to the square root of x squared plus y squared. And the direction of this is arctangent y over x. Take note that there will be a right triangle that can be formed. Using the Pythagorean theorem, we can get the magnitude and the direction using SOHCAHTOA. Let us get the magnitude and direction of both. For the magnitude of A, vector A, so we'll have 1 plus 4, right? We have square root of 5. That is the magnitude of vector A. The direction of vector A, we have arctangent over -1. We have arctangent of -2. In linear algebra, it's fine if we will not get the exact value of arctangent -2. Whichever value comes from the calculator, just adjust it because this one is arctangent function. It doesn't cater all the possible values because it is only limited to a certain domain and range. Okay? In linear algebra, it's fine if you will write arctangent -2. For the second one, vector U, the magnitude of vector U is 4 plus 4. We have here square root of 8, so that is 2 square root of 2. And then for the direction of vector U, we have arctangent of -2 over 2. We have arctangent of -1. This is a special angle, so this is -pi over 4. This is it. -pi over 4 or 45 degrees. Next, let's have the vector addition. This is one of the primary vector operations that we'll discuss in this chapter. The sum of two vectors u and v is obtained by adding their corresponding components. That is, if we have here vector u that has components u1 and u2 and v1, v2, then their sum vectors u plus v is equal to this one, u1 plus u2, comma, v1 plus v2. We're just going to add their corresponding components. Geometrically, the sum of two vectors can be represented by the diagonal of a parallelogram with the two vectors as the parallelogram's leg. As you can see here, we have vector u and vector v. We can actually extend or replicate the vector v here, parallel, and then vector u here. And then when we draw the diagonal connecting the origin to the point where they meet, that is actually the sum of the vectors. These are the properties of the addition of vectors. If u and v belong to the same vector space, then the sum of them will be in the same vector space. We will discuss vector space in the next lecture video. This is the closure property. Vector u plus v is equal to v plus u. This is the commutative property. It doesn't matter which order. And then the associative property, if we have three vectors here, you may add u and v first and then add w after, or you may add v and w first and then add u after. And then last, we have the additive inverse property. U plus negative u will result to the zero vector. Let's have the following examples. Letter A, vector u 3, negative 1, and v 1, 5. Alright, so let us write the sum of them here. Okay, the sum of them will be the vector containing 4 and positive 4. Right? 3 plus 1 is 4, negative 1 plus 5 is positive 4. Let us try to verify whether the parallelogram law is true. Vector u, this is vector v. Okay, let's copy the parallel sides. Okay, it's fine whether it will go beyond because we're going to erase it after. Okay, what is this? Okay, as you can see, this is 4, 4. Right? So this is 4, 4. This is the sum of their vectors. Next, without graphing, let us find the sum of u and v. Okay, here we have 1/2 plus negative 3/4, so that would be negative 1/4. And then next, we have 3/2 plus 7/2, that will be 10/2, 5. I will leave to you letter C as an exercise. Next, we have the scalar multiplication. If vector u has the components u1, u2, and c is not equal to 0, c is any real number, then c times vector u is equal to the following. The components will now be cu1, cu2. Meaning to say, you're just going to distribute the c to the components. Geometrically, the scalar factor makes the vector longer or shorter. In this case, we have vector u, the original vector. If we multiply 2 to it, the components will double, right? From 1, 4, it will become 2, 8. Then, the magnitude of it will be twice of the original vector. Take note that c here is a real number. Meaning to say, c can assume any value as long as it is not imaginary. Okay, like square root of 2, c may be square root of 2, 3 over 2, and even with numbers with decimal places. Vector A, we have vector u, 3, negative 1, v, 1, comma 5. Let's find the 2 times vector v minus 3 times vector u. Okay, this is equal to, don't forget to write always the thing that you are getting. Here, I will write the vectors in the matrix form. We have here 1, 5, and then minus 3, okay, performing the multiplication, we will have 210 minus 9 and negative 3. Be careful. Take note that I only multiplied 3 here. I left the subtraction symbol here. Okay, what will be the answer? We have 2 minus 9, negative 7. 10 minus negative 3, that will be positive 13. This is now the result of the operation. I will leave letters B and C to you as exercise. These are the answers for letters B and C. Now let's talk about the dot product or the inner product of two vectors. Given u and v, their dot product u dot v is equal to u1 v1 plus u2 v2. Take note that the dot product is a real number. Our answer here is not a vector, okay, but a real number. For example, we have vectors u and v. Let us get twice of vector v dot u. Okay, what are we going to do? Let's answer letter A. In getting this one, the dot product of u, v, and u, we must perform first the scalar multiplication of 2 and v. So this becomes like this. And then dot 3, negative 1. Take note that when getting the dot product, we must write the symbol for it so that your readers will know that you are performing that product here. 6 minus 10. Is that correct? So 2 times 3, that is 6. And then 10 times negative 1, negative 10. We have negative 4. I will leave the exercises B and C to you. For letter B, we have vectors with fractional components, and for C, we have here another concept. Two vectors are orthogonal or perpendicular in R2 if their dot product is 0. That is, u dot v must be 0 for them to be orthogonal. Graphically, they would look like something like this. So these two vectors are orthogonal. Also, when we rotate it like this, these vectors are also orthogonal. Now let us extend our discussion to Rn. A vector in Rn is an ordered n tuple in the Euclidean n space in the form x1, x2 until xn. You may write your vector in the parenthesis form or in the matrix form. These are what we call the Rn or n space. First, we have R1, 1 space, the set of real numbers. R2, 2 space, set of all ordered pairs of real numbers. R3, ordered triples of real numbers until Rn, set of all ordered n tuples of real numbers. The operations in Rn or n space, The addition and dot product of two vectors in R2 are all applicable in vectors in Rn, provided that the two vectors both belong in the same vector space. So the closure property must still be observed. For example, vectors A has two components, vector B has three components. We cannot add them because they do not exist in the same vector space. A belongs to R2 while B belongs to R3. Next, the dot product of A and B here does not exist as well because A belongs to R3 while B belongs to R4. Make sure that the closure property is always observed. Now let's have the vectors in R3. Vectors in R3 may be drawn using the Cartesian coordinate space. From the illustration, represent point P as a vector. This one is three-dimensional, okay? Your imagination must be working here. Vector P, let us write the components of vector P. X, Y, Z. Let us write the coordinates of the point. Hence, the components of the vector. The x here will be, this is your x-axis, so the direction will be going here. This is your point. 1, 2. The y here will be, from going to this direction, 1, 2, 3. And then the applicate or the z coordinate, we have, from here going upwards, we have 1. This is the representation of point P as a vector. Now let's discuss about the Cartesian coordinates in space. The three-dimensional Cartesian coordinates in space has three coordinates x, y, z. So this is the ordered triple. Okay, x first, followed by y, and then z. The space has 8 octants. Okay, this one is what we call the octant. 1, 2, 3, 4, 5, 6, 7, 8. 4 octants above and 4 octants below. It has 3D two-dimensional planes in pairs of axes. The color green, this is the YZ plane. The color blue, that is the XY. And then the flat one, the color pink or red, is XZ. Those are the two-dimensional planes that can be formed using the axes. You are highly encouraged to answer this exercise. Always take note that when writing a vector, here in the computer, of course, we may write the vector as a bold letter. But when you are writing it on the paper, you may just use the harpoon or the arrow one.